written extensively on databases and other technology matters on Quora and has been a top writer there for the last 3 years. I think this is an exciting opportunity for all our students to hear from the horse's mouth about the internals of a database that they often use. So let us start with his talk.
Hello. Hello. So, I'm Greg Kemnitz, and okay. Hello? Okay. So, I'm Greg Kemnitz, and I basically got started in databases, while at Postgres in the late 1980s, and have been doing stuff of that kind pretty much ever since. And, in case you don't know, Postgres was started by Professor Stonebraker, who is a pretty well-known guy in databases at that time. And so Ingress was basically, the Ingress database was the original database done by outside of IBM that was used the relational data model. And excuse me. And Ingress was basically Professor Stonebraker's first successful research project. And after, with the success of Ingress as establishing the basic relational data model for out in the world, Postgres, Professor Stonebraker came up with the idea of Postgres as a way to extend the relational model to support multiple data types and multiple different ways of accessing data. Postgres coding began in earnest in 1986 with the publication of Professor Stonebraker's sort of paper, The Design of Postgres. And the Postgres used the post-COIL query language that was based on the COIL language used in Ingress. And it was so long ago that SQL didn't really exist yet. And so, and in a lot of ways, COIL and post-COIL were actually nicer languages than SQL in a lot of ways. But because SQL was championed by Larry Ellison, it won. Yeah. And so I will move on to the next slide. And Professor Stonebraker was basically one of the three, you could argue, founding fathers of relational databases. And you had Edgar Codd and Date as kind of the main theoreticians. And Professor Codd led the initial implementation of System R at IBM. And Professor Stonebraker led the implementation of Ingress at UC Berkeley. And basically between the three of them, they kind of established the relational model and the basic architecture of relational databases that is still pretty much used today in all, including like Microsoft SQL Server and pretty much all the guys. And kind of like one of the things that's interesting is Ingress or Postgres have little bits and pieces of themselves in pretty much all the commercial and open source databases that are used in the world. And Professor Stonebraker is now at MIT, but spent about 20 years at UC Berkeley, and that was where he did Ingress and Postgres. And along the way, he founded various companies, some more successful than others, but he's done well enough that he has a very good life now. So, and VaultDB is his entry into what's called the NewSQL space, which are kind of the NewSQL databases are basically post-System R databases that are more distributed than the classic relational databases that are kind of monolithic single node entities. And Professor Stonebraker won the 2014 Turing Award for achievements in database technology over his career. And back here, the fan won't blow so hard. But yeah, so basically, the Turing Award is essentially the computer science equivalent of the Nobel Prize, and it's comparable to it has an honorarium about the same size as Nobel Prizes do, so it's a big deal. And so the Postgres project itself had, several big research ideas, and one of them was the having user-defined data types at the table level. So the idea there was you wanted to be able to extend the database by writing some C code that just defined the various relational, defined the basic comparison operators and an in and an out function. And then the database would just use those and store them and would be able to index them and do all that kind of stuff with them in such a way that it'd be very easy to add new simple data types as well as complex data types to the database engine. One of the other research objectives was exploring various kinds of rule systems in the database. And in those days, databases often didn't have generic rule systems. They tended to have pretty much hand-coded things for stuff like views and triggers. And Postgres, the idea of having a general-purpose rule system was to allow for these kind of operations to be done, just from general rules. Another objective was the time travel archival storage manager. The idea there was to allow the database to have versions of rows, and the rows would basically keep track of a history of rows and also a general history of the world, and to also support archiving from expensive spinning disk to cheap tapes or other kinds of cheap storage at the time. And actually, I guess I just described the multi-tier storage manager, but that was the idea, was to have different tiers of storage so that you could have like a really huge database, some of which lived in a tape drive or a worm drive at the time. And the other thing was basically the idea of allowing table types and various other kinds of types, which initially were called extended relational. And the last big objective was to just give a software test bed so that researchers and interested parties could play around with a code base that was a real relational database and could do various interesting things on it and do analysis to write papers and get their PhDs on their research that they did with the product. So the research accomplishments of Postgres were that user-defined types worked. Yay! We got them to work, and they worked the way they were supposed to. And in a weird way, it was a bit tricky because things like dynamic libraries, which is how you would implement that kind of stuff now, were only sort of existing in those days. The other thing was the query rewrite rule system worked spectacularly, and the idea of the query rewrite rule system was to kind of take the query you give it, and if that query would visit something that involved a rule, the query would be annotated with the rule text, and then that query plus the rule would actually be the thing that ran, and that was how Postgres implemented views. And the time travel storage engine kind of worked, but I'll get to the kind of part in a bit. But it worked well enough to prove that the idea was feasible. And the object relational idea actually did work pretty well, even though there's a kind of interesting story about that I'll tell in a bit. And one of the other big thing was Postgres had the first implementation of R trees, and which are used for spatial queries. And R trees had existed already, but they had never been used in a relational database before. And one of the other big things which Joe Hellerstein, who's now on the faculty at UC Berkeley, did was a query optimizer to account for the different costs of data types. Because before then, it seems like an obvious idea now, but Postgres began to have things, blobs and other kinds of data types that could be big. And so because they were big, they would have different costs to access than more ordinary data types like simple ints and strings. And so, the idea was that now you would have cost functions for all these different kinds of accesses and not just treat everything as the same cost. So the multi-tiered storage, this is the negative results of the Postgres project, and it's actually always important in any kind of thing you're studying to learn about things that didn't work as well as things that did. And so one of the big negations was the multi-tiered storage engine only kind of worked, and one of the ironies there was because often this kind of research is ultimately driven by the economic imperatives of the day, and during the time of the Postgres project, the price of hard drives crashed massively, and so it turned out that the multi-tiered storage approach really wasn't all that interesting because disks just got cheap, and disks getting cheap has been continuing to this day. And in those days there was no such thing as petabyte databases, but still, that was why we didn't put a lot of effort into the true multi-tiered storage engine. And the time travel support in the storage engine was only kind of half there. And one of the big things that we did that would have made it more interesting would have been to have indexes be able to index the time travel parts of the data world. But we didn't do that. And we probably should have, but we didn't. And one other thing that was interesting was we had two rule systems. One was a query rewrite rule system that worked. The other one was a kind of low-level, tuple-level rule system that functioned correctly, but so massively messed up the code that one of my jobs at Postgres was to ultimately, after the guy got his PhD on it, I kind of had to rip it out. Yeah. And one of the other things that we found out is don't use Lisp for your top level, because it's very bad and very slow, garbage collection. The interface between Lisp and C, especially in those days, wasn't very good. We did have one thing that was actually good about using Lisp, though, was that we ended up using S expressions for storing all the parse trees and query plans and execution plans. And to this day, if you look at PostgreSQL source code, you'll still see S expressions in there. And it's kind of an interesting bit of archaeology that a design decision that was made 30 years ago still has a pretty big footprint in a widely used piece of code now. So, and what was my job at Postgres? Well, one of my big jobs was to fix bugs, because to a certain extent, part of the organizational structure of Postgres was that the grad students should work on code directly related to research, and since we actually had external users, it was basically the duty of staffers like me and a couple of other guys to fix bugs and do kind of maintenance and ongoing support, because grad students shouldn't be doing that kind of thing. And so that I kind of also developed a QA world and maintained it, and also managed bundling up Postgres so that someone could download the Postgres tarball and install it on their local machine. And in those days, you didn't have really pretty installers like you do now, so like it was just, untar it and type make and hope it works. Yeah. Yeah. And one of the other things is, grad students have pretty widely differing skills in coding, because often like you could be really good in taking exams and things, but sometimes your coding skills weren't really fresh, especially in those days, because in those days it was actually pretty hard for people in countries that are in universities that weren't highly wealthy and didn't have a lot of physical infrastructure to do a lot of coding, because PCs were still brand new, and the idea of having like a bunch of VAXs or a bunch of mainframes for undergraduates to use was pretty much only in the top universities in the world at the time. So like, it's kind of hard to imagine now where everybody has a laptop when they're 5 years old, but in those days, often grad students would show up at the project with having written maybe a few hundred lines for a senior thesis in terms of coding, and that was about it. And all their other work had been pencil and paper. So, I kind of had to help them deal with a 200,000 line code base that someone said, here, do something cool with it. And so that was one of my ongoing things to do. And kind of like I talked about before, I did do a fair amount of code triage, which is basically the idea that you kind of evaluate a piece of code that a grad student developed and figure out, is this something we want to keep and maintain, or is this something we want to kind of quietly let go? And about 70% of the code we kept, about 30% of the code we would let go. And it wasn't always because it was bad code. Sometimes it was because the code compromised the layout of the database engine, because it was like, messing up the flow or whatever, but still achieved an interesting research result. And probably the main piece of code that I did independently was I had to write the code that actually loaded the user-defined data types from built binaries into, basically I had to write what you now would call the DLL or shared object loader in an operating system, because they were sort of implemented in a few OSs, but there were a whole lot of OSs that we wanted to support where they didn't exist, so that was the main hunk of code I wrote. And at the end of the day, one of the things I was oddly kind of proud of was when I got to Postgres, there was about 220,000 lines. And when we handed Postgres off to Illustra for its first commercialization, there was about 170,000 lines. And I pretty much ripped all that out. Yeah. And I also ANSI-ized the code. The code was written in good old-fashioned KNR-C, and I had to ANSI-ize about 50,000 functions and fix a few hundred bugs we found when we did that. So just a whole lot of just getting it all to flow nicely. And so, like I said, we had various adventures along the way. One of them was the Lisp misadventure, which almost killed the project because it was just, we couldn't show results to the people who would give us money because Lisp was such a pain in the whatever. So after ripping it out, we managed to keep the project going and keep the funding flowing. And one of the other things that was kind of an interesting story was in those days, Valgrind and other kinds of C memory debuggers didn't really exist yet. So if you had a memory leak or you had memory corruption, You just had to figure it out by hand. And those were often some of the worst bugs, where like you could take like a week to like do crazy things like, stick, 20,000 printfs, it seemed like, all up and down the code, and do all these kinds of tricks to figure out what made this crash and what didn't. And so there was a startup called Pure Software that had a product called Purify, and it was the very first memory debugger that I ever used. And I ran it, and I found like 30 memory corruptions and 10 memory leaks in the very first try, and the reason that's kind of an interesting story is that the guy who founded Purify, went on to ruin his career by founding a company called Netflix, and he is now richer than God. And so I actually got to meet him, and we were actually an alpha user of Purify, so I actually got to meet him for quite a bit as we fixed bugs. And one of the other things that was my job was to interact with our customers, including some DoD types. One of my favorite customers was a lady who was doing something with Tomahawk missiles, so I made darn sure that her bugs got fixed, because I don't want bad things happening with Tomahawk missiles just because Postgres decided to be unhappy, because I don't want her targeting my house. And one of the things that was kind of fun was my university phone number was actually 642 RTFM. And if you know what RTFM in the nerd world means, read the fine manual. And so that was why I always wrote it as 642 RTFM in the user guide that we had. But like I said, be nice to customers doing stuff with cruise missiles or other sort of military things that they don't want to tell you about that they're having bugs on. Yeah. And one of the more interesting stories is, why is it object relational and not extended relational? Well, if you read the early Postgres papers, its general approach is described as extended relational. But around 1990, Professor Stonebraker went to one of the big funding meetings in DC, where there's various guys with lots of stars on their shoulders and that sign big checks. And he discovered that University of Wisconsin was getting a lot of funding for a hot new object-oriented database that it was developing. So after he came back, he marched into my office and said, "Extended is now object. We need to add OIDs, we need to add inheritance, table inheritance, multiple inheritance, all this stuff that object guys love." And so we did. And the irony was it ended up being an actually interesting researchy thing to do, but the roots of it were basically, Professor Stonebraker being afraid that we'd lose our funding because we didn't have a big O in our research stuff. So, and then there was always the terrors of triage, because, a programmer who works really hard on a piece of code obviously loves it, because I love my code. If you don't love your code, you're not a programmer. Yeah. But sometimes, like I said, sometimes we had to figure out various things to take out of the code base because they didn't work, or they were just wrong for the product, or their research efforts were over. And I usually tried to wait until whoever it was got their PhD or master's and moved on, but sometimes I'd have to say, this has to go. And those conversations were never particularly fun. But yeah. So, and after the university, the Professor Stonebraker founded Illustra, and I stupidly didn't join Illustra immediately, but I did become a consultant for it about a year after it started. And Illustra was the first commercialization, and it was eventually bought by Informix, which called its Postgres Universal Server, and then IBM bought Informix, and you will still find the Universal Server in IBM's product catalog, although it's actually not part of DB2, but it is part of the general IBM database product catalog, and is apparently used by various spooky things in the US government. And basically the ADTs were called data blades by IBM, and they had various different ones for all kinds of it tended to be mostly used for manufacturing purposes, where they would have custom data types to do various tracking of manufacturing things. And then the other commercialization of Postgres that was successful was Greenplum, and Professor Stonebraker had nothing to do with Greenplum, but it was bought by EMC for a whole bunch of money, and Greenplum actually pioneered the use of Postgres for what is now called cloud and data mining, because Greenplum was an early cloud solution, and I think EMC sold Greenplum again. It's no longer part of EMC, but all the people at Greenplum were very happy with it getting bought for probably about twice as much as it should have been. But yeah. Yeah, if you want to get bought by somebody, get bought by EMC. They tend to overpay. Yeah. And then came the open source Postgres, which was started by Andrew Yu and Jolly Chen, who were some of the last grad students to work at the Postgres Project. And they came up with something called Postgres version 5, and Postgres version 5 became PostgreSQL version 1 in 1994. And they, as you can kind of tell, they ripped out PostgreSQL and replaced it with SQL. And basically, in a way, it's unfortunate, but it is also true that Postgres is mostly a true open source project without a lot of enterprise support. There's a company called Enterprise DB that supports Postgres, but it's certainly not like Oracle supporting MySQL. And basically, Postgres is now fourth in the DB Engine's rating right now, and ahead of MongoDB, which is always good. Yeah. But yeah, I mean, and Postgres is actually getting a slow up ramp of popularity, especially as MySQL got bought by Oracle, and a lot of people don't really like that. Now that I'm actually transitioning to the next phase of my talk, which is kind of comparing Postgres and MySQL. And contrary to what it may sound like, I'm not going to totally be a Postgres fanboy, because I will grudgingly admit that there are some things MySQL does better. So they're very different kinds of database engines, and they come from very different backgrounds. And one of the big differences was MySQL was basically kind of a pioneer of the freemium movement, where you have an open source product that's basically championed by an enterprise, and you make your money by selling support and maybe fancy GUI tools or whatever. And that was how MySQL AG made money. And basically, MySQL AG was bought by Sun, and then Sun got bought by Oracle. And Sun spent $1 billion on MySQL, which made my jaw drop, because MySQL AG never made more than about $20 million a year. So, but it probably was a wise investment for Oracle to kind of take it over. And so Postgres, so the big difference between MySQL and Postgres is all about queries. It has really awesome query capabilities, and vast numbers of join answering capabilities. It has hash joins, it has merge joins. It can do all that kind of fancy joining things. Whereas MySQL is mostly about ease of use for administrators and has lots of deep support in the industry. So the MySQL advantages, now there's one big advantage of MySQL in terms of the actual running of the system. The InnoDB storage engine really is annoyingly better than the Postgres storage engine. And the reason for OLTP applications, and the reason for that is because, remember I talked about how Postgres has this versioning stuff and the time travel stuff? The remnants of that is something called the vacuum cleaner. And the vacuum cleaner is basically a storage garbage collector. And storage garbage collectors really aren't really great if you have a 24/7 high traffic website where you've now got to figure out when do you run the storage garbage collector and how do you deal with the fact that it's going to make your database about 50 to 75% slower. And it's also, InnoDB is also an index organized storage layout, which means that basically, unlike a traditional heap where you have primary keys or just a special kind of secondary index, in InnoDB, the actual base table structure is organized around the primary key in a native B tree. And if you are really evil, you can do all kinds of cool tricks with that to make stuff go fast. MySQL has a very lightweight process model, where basically, single instances can handle lots and lots of concurrent connections. And so basically, each connection to a MySQL instance only needs a thread inside the actual instance itself. And also, MySQL kind of has a more sort of developer or sort of end user friendly tradition as far as dealing with a lot of users that want to have really unusual, like insert ignore, where you can like do a bulk load and you can ignore primary key collisions. And that sounds like a dangerous thing, but it actually can be useful in a lot of applications. And in fact, in my last company, we used that for application level crash recovery. But Postgres only recently put that in. And Postgres does have a bit of a paternalistic attitude towards users, where they kind of say like, well, you don't really want that, you should just do it right. But a lot of users really don't like that attitude. But the big disadvantages of MySQL is it can only do nested loop or nested loop over index joins. It has no hash joins and has nothing else. So it really does kind of suck in queries. And you can do really dumb things like you can write inquiries that in MySQL would finish in a few milliseconds, that in Postgres would finish in a few milliseconds. In MySQL would take hours to run because constant subqueries in MySQL are actually fully evaluated every time a row comes in the outer part of the query. So if you have a 10,000 row inner query with your in, and you have 1 million rows visited in the outer query, you'll have a 1,000,000 times 10,000 comparisons done, which sucks. And it allows a lot of bad things in its default modes, like illegal group by queries that appear to work, and a bunch of other things like that. So querying is definitely its weakest part. And like I said, Postgres has just awesome querying. If querying is what you need to do, and if you need to do really icky querying, get Postgres. Postgres has a lot of newer SQL features like CTEs supports the SQL standard much more nicely than MySQL does. And Postgres has really awesome support for JSON and specialized indexes that MySQL doesn't. MySQL has some now, but not as much as Postgres. And the disadvantage, probably the biggest one in some ways, is Postgres has a pretty heavyweight process model, where like each connection to the database gets its own full process. And you can kind of mitigate that by using connection pools, but it still means there's a pretty low ceiling on how many active connections you can have in an individual machine before it kind of goes bad. Yep. And the vacuum cleaner is an ongoing headache, and if you have a really, really, really big world. And Uber recently switched from Postgres to MySQL, and the vacuum cleaner was their main objection to it. And because Uber has a very OLTP-ish workload, and they just couldn't figure, because Uber tended to have just one data world for the entire Earth, so they never have downtime to do that kind of thing. And Postgres does all of its storage replication in the storage engine, whereas MySQL actually does its storage replication in the query processor. And that has many advantages and one big disadvantage. The big disadvantage is it won't do commits exactly right. But the advantage is that you can do the storage plugins in MySQL and not have to worry about replication because it's handled above you in the API stack. And so where are these guys used? I guess you can probably see where I'm going, that basically if you're doing data mining and analytics, Postgres just kicks butt because it does really nasty queries really well. And in data mining, you're going to tend to have a lot of ugly queries, a lot of big queries, a lot of ad hoc queries, and you might not want to futz around with tuning the queries a whole lot. You just want to get your analysis done and be done with it. So you can write your R script that's going to call Postgres and load the data set in and you chew on it. And kind of like I said, Postgres or MySQL, for various business-oriented and technical reasons, kind of owns the web, especially since much of the web is very OLTP-ish. And so basically, kind of the sad part about these things as a Postgres guy is that the query parts, the query badness of MySQL, you can actually work past, because in these OLTP application environments, you can hand-tune the queries and just make sure they work. But you can't fix the storage engine and you can't fix the connection model. There's just no way to do that in your app. And so that was why, ironically, in my last company, we actually used MySQL, was because we had that kind of workflow. And Postgres actually can and is used in a lot of web worlds, especially ones that are related to blogging, because these worlds tend not to be super OLTP oriented, and often have, you can go ahead and run the garbage collector and you don't have giant numbers of connections to individual instances. So, yeah. And this has actually been one of the ideas that I've been kicking around is why not take the Postgres query world and kind of disembowel MySQL and throw out its lame, sucky query world and drop basically drop the Postgres Ferrari engine into the truck of MySQL and make a really fast-going truck. So I've kind of studied it some, and it would actually be, if you did it that way, I actually do think it could be made to work. It'd probably take about a year to do, but it would actually solve a lot of these problems and a database world where you didn't have to figure out, oh, do I use Postgres here, or do I use MySQL here? How do I pick which one? And, just have one thing that is just awesome for everything. And, like I said, I just wanted to get rid of this false choice that I felt like I had, where I really wanted to use Postgres, but I had to use MySQL because its storage stuff worked better. And, I'm now getting to the last part of my talk. Hopefully I'm not putting everybody to sleep. But basically, one of the big debates in the world has been the relational versus NoSQL. And basically, MongoDB, can you get away, is relational basically a dead technology about to be swamped aside by the awesomeness that is MySQL? Or will there be coexistence in peace and tranquility? And one of the things that's odd is often these debates have nothing to do with technology. It's more one of these, it's just cool. It's the new thing. It's awesome. And you're using this thing that came from the 1970s. And we are just so awesome and advanced and avant-garde, et cetera, et cetera. So the real answer in a lot of this stuff, often these debates talk about what I kind of think is almost a kind of red herring, where people talk about acid properties and stuff. But in a weird way, I kind of regard that as more of an implementation detail than a real differentiating factor. Because the real issue is, how do you represent links between data? Now, the link between data is basically, how do you get the data that's related to the record that you're anchoring on? Like, how do you get your department from your employee record? And one way you can do it is with something called a hard link, where you actually have a physical link value in your employee record, and there's a disk pointer that basically points at the department record of the department you work in. And those are basically used by graph databases and codicil databases from the 1960s. And also object-oriented databases use something like that by using OIDs, which are still basic. They're not really hard links because they're using the OID mapping world, but they're still basically links between actual physical objects and still need to be manually updated the same way hard links do. Proximity links are basically what you have in something like MongoDB, where you have a big bucket of stuff that is related. So like if you're going to store the employee and department stuff in MongoDB, you would just have an employee document with like the department record and the employee record just sitting in that document together, and you would just not worry about normalization. And a computed link is basically what relational databases do, where the links are actually defined by the query itself and are not really native to the data manager. And these are basically the three things that drive what you want to use. So with hard links are very fast, and they're very good for walking around complex data structures that you want to have with like complex trees or graphs or that kind of thing. And they also kind of make sense to programmers because they're like C pointers except stored in the database. And that was why object-oriented databases ended up using something like hard links, because they were using that for the persistent object store. Now the disadvantages is, now let's say you change your department. Now you got to refactor that actual link to have the new department pointer. And if you forget so like if you're changing a whole bunch of employees to a new department and you forget one, now you're just kind of broken, because now you have what is basically a corrupt database. And the other disadvantage of hard links is they don't support wide-scale distribution very well, because traversing a link is supposed to be cheap, and if the thing you're linking to is in a different node, you're going to have to cross a network to get it, and that's not fun. Now, proximity links are actually the fastest possible thing, because you just have everything sitting in a document, and the document is in one physical piece of storage. So you just suck it up, and there it is. And you don't have to do any kind of traversal or walking or anything like that. And this is proximity. You probably haven't heard of proximity links, because it's something I kind of made up, that it describes how stuff is related in a document, I think, as well as anything that I can think of. And also, you have a pretty high degree of schema flexibility with documents, because documents are basically their own little databases by themselves, and you can store all the metadata in each document by itself. And one of the things that is the big excitement for a lot of people with document databases is they distribute really, really awesomely, because they have fundamentally a shared nothing relationship between documents, so it doesn't matter what node it's in, and you can have 1,000-node data world with a document database pretty trivially. Well, not trivially, but it'll work. And the disadvantages of document databases is that if something inside the world changes, you actually have to visit all the associated documents and edit them with your application code to make them correct, which is not fun. And it's also really hard to do reporting on a document database, because it's very hard to reach in and pull anything out other than based on the anchor key of the document or whatever you happen to have indexed in the document. And basically all the related data has to be physically stored together, and you can kind of pretend to do joins with document databases by storing IDs that point at other documents in a document, and you suck it into your app, you pull out the IDs, and then you go get it. Then you have a sort of an application managed join procedure, but that's kind of sucky way to do a join. And obviously, you're not going to get any support from the database for doing a join like that. And so, then last but not least is computed links, which is what relational databases do. And their advantages is that all you got to do to update all the employees in a department is just do an update statement, and you just do it. And you can just, because everything is computed, you don't have this icky problem of refactoring a bunch of things. And you can also do, one of the underrated things in databases is any real database is going to have reports done on it, because business people are going to want to know what's going on with the data world. And pretty much by definition, you're not going to know what reports need to be done until like the business people ask you for them. And relational databases are awesome for ad hoc querying and reporting, and because basically analytics is, in a weird way, is just a fancy name for reporting, because it just has more data, but it's still basically reporting at the end of the day, or at least in business analytics. And links can be, and because you can figure out how to do links, that you can have join methods that are really optimized for rapid traversal of the links, and the mechanism for answering the query is computed dynamically, which is really awesome. Now the disadvantage is you can't. It's hard to do a multi-node data world with a relational database unless you do some kind of policy level sharding at the app level. And that's actually not a horrible thing. You can have a pretty huge data world if you do it that way. And link, and the other disadvantage is link traversal is a bit slow because it has to actually be calculated. Although if you're traversing lots of links, like in a big join, it will actually be faster. And SQL-based databases tend to have centralized schemas that are a bit heavyweight and need, may need downtime to do updating. So, which one to pick? In the vast majority of applications, you probably ought to initially consider a relational database just because, you just should. If you're going to use a NoSQL database, you should have a good reason for doing so because of a lot of the inflexible nature of a lot of them. But if you need a NoSQL database, you probably know you do, and it's because you have either a giant amount of data or you have some kind of access pattern that is very friendly to a NoSQL database. And for a lot of, and nowadays, a whole lot of big application worlds are basically best of breed, where they have some parts of it, the parts they want to do querying on, the parts they want to make sure they have ACID transactions and stuff. Those are all in relational databases, and then some other parts are in things like MongoDB or other OODBs or other NoSQL databases. And like Netflix has a whole lot of its descriptions and a whole lot of its text stuff in MongoDB. Also, all of its logs are in MongoDB. But all of its stuff related to billing and users and that kind of thing is all in MySQL as it happens. So, and one of the other things that's interesting is relational databases actually, most new relational databases actually support JSON now. And so you can actually have a JSON column type. And Postgres in particular has a really elegant implementation of JSON because Postgres supports something called partial indexes. And so you can actually index stuff inside your JSON document and do efficient searches on it using those. And there are true NoSQL applications, but they're very rare. And often they're not using one of the standard NoSQL implementations. Like you could argue Google is a NoSQL data world, but Google wrote. Okay. Cool. Okay. Sorry. Anywho, this is the last slide anyway, so I'll just go with it. So basically, so most of the really big NoSQL worlds are also just have hand-coded databases or data managers like Bigtable at Google. Yeah. And this slide will probably look really ugly, but I'll go through it. Okay. Well, and that's the end of my talk. And hope you enjoyed it, and we'll open the floor for questions. Why did they take off? They kind of didn't actually. Well, I mean, they found very good niches because OODBs are very good for representing. Like if you have a car or you have like a piece of industrial equipment that you're doing CAD/CAM on, OODBs are actually really great, and they're really great if you have a whole lot of different kinds of stuff in your data world and you want it to all be physically related to each other. So like you could actually like completely describe everything in a car in an OODB, and you can actually navigate around inside your car representation very efficiently. So OODBs are really awesome for those kinds of use cases. And several of the object databases still exist that were founded in the 80s. And that's basically their niches in kind of CAD, CAM, and industrial engineering applications. Does that answer your question? Yeah.
So I have a curiosity about legacy. Did Professor Stonebraker ever write a code in Postgres?
The question is, did Professor Stonebraker ever write code in Postgres?
Yes.
And the answer is, not to my knowledge. Certainly he didn't when I was there. But one of the things that he did have was, he had a pretty awesome mental model of the Postgres code base, to the point where we would have our weekly meetings and we'd be talking about bugs. And he often would say, the bug is that. And about half the time it was that. So he had a really awesome mental model of the code in his head, even though he never actually looked at a page of source code to my knowledge.
The second question is, where does Oracle win here? I mean, is it because of the enterprise support, or is the technology better in any of the way? Is it anything better compared to Postgres and MySQL?
And the question is, why did Oracle beat Postgres and MySQL? And the answer is basically, Oracle did several really good things early on, and one was they supported SQL natively before RTI did, and that Relational Technologies was the commercialization of Ingress. And how Ingress supported SQL was they actually had a translator that translated SQL to Quell, and then Quell was what was actually run. Now, the irony was that actually still ran faster than Oracle, because the first versions of Oracle were really slow. But Oracle, Larry Ellison knew selling, and he said, we have native SQL support. Ingress is just a translated thing that has a veneer of SQL on top of this thing that they're using internally. And so that was one, and Oracle was also really awesome at basically selling, and with various things that are interesting. And so basically, Oracle, and so Larry Ellison just pushed hard with his sales team and was much better at sales and marketing, and the engine worked well enough. So it was a classic case of the thing that was well enough, marketed very well, beating things that were probably better, although RTI did make one critical error, which was they actually decided to try to rewrite the engine to be faster and to have native SQL support. So they essentially shut down the company for a year to rewrite the engine. And by the time that was done, Oracle had basically taken over the universe. And that was all she wrote. So, did that answer you? Cool.
Maybe a third one.
Yeah.
SQL is a standard, like a fixed thing. Is NoSQL a fixed thing, or it just like essentially it's a schema-less database? Anything that supports schema-less thing is just NoSQL. Is that what NoSQL is, or is it like do we know really?
Well, you're not going to find anything. You're not going to find a standards committee that says we're the NoSQL standards committee, because it can't exist. It's like saying, this is a no Hindi language we're speaking, because it's English or Chinese or anything else.
So it's not anything consistent. It's not anything that's probably not relational and schema-less, supports schema-less data is probably, you can claim it's NoSQL. Is that how it is really? Yeah,
pretty much. And pretty much until 1971, all databases were NoSQL, by definition. But in practice, NoSQL generally refers to document databases or graph databases for the most part. So if you want to kind of wrap your hands around it a little bit, you can say MongoDB or any of the graph databases or Cassandra are the NoSQL databases. And so I guess, let me state your question that it's, my job is to basically kind of supervise the grad students' code and sort of protect the code base in some ways, and should other research projects adopt a model like that. And my answer would be basically that it's an expensive approach, because one thing, you actually have to have money to pay someone like me. But if it can be done, it might prove to be a good way to do things for a really big, complex code base, especially if the research project itself is based on having a large, complex piece of code. Although one thing I dare say is grad students probably have a lot more experience in programming now than they did then, because nowadays you can't graduate from any computer science undergrad curriculum without doing a whole lot of actual programming, which wasn't actually true in those days. So, is that an answer?